We got it.
But for those of you who were not in Stinger, I want to make sure that you have access to your answers, so have them out. What we're talking about today, and we're taking this in baby steps. So, if all things go right, you walk out of here today with your homework finished. Because the lesson is quick and short. It was one of those, it was too big for one lesson. So we broke it into teeny tiny parts. It's like a little half lesson today. That's what you're getting. All right. So if you look at each of these, the whole concept here is that we're finding the area under the curve. And you can't take the area of these curvy graphs. So what we started doing is dividing them up into little rectangles. And we found the more rectangles we used, the more accurate we were able to be. So then we needed to add up all those areas to get the total. And then it was tedious. There's a lot of them. So we wondered, is there some calculus that can help us figure it out? So these two things say the same exact thing. If you want to think about for linear equations, you can have the standard form or the point slope or the slope intercept of a linear equation. All means the same thing. One is simpler than the other. And each format kind of tends towards different kinds of problems. So same kind of idea today. This sigma means the summation of. So we're adding up all the little rectangles, and those rectangles are the result of however wide our rectangles are, and then the output of the function represents that height. So our function here is an inverse variation function. So when you were in Algebra 1, you learned direct variation. So your direct variation function was your y is equal to kx. And the examples that we use for them were always, you get $10 every time for every hour you babysit. You get $5 every time you walk your neighbor's dog. You get, so this constant of variation, we know is the slope. So the direct variation is that equation that goes through the origin. Then we went around and talked about inverse variation, and that was where y is equal to k divided by x. And that x is down in the denominator, and that's the one that we use all the time when we're trying to find all of the factors of a number when we're factoring. I used to tell the kids, go into the calculator and enter into, so do this with me now, get your calculators out, go into function screen, and if you enter 144 divided by x, no, get up and get your own. No, I'm not watching you do that. Get up and get your own, or do the lesson without a calculator. That's disrespectful. So if you go up into your y is equal to, and then type 144 divided by x, and then go to your table of values, and there you see all of the input output numbers. So what you do here is our inverse variation, and this was always our trick that we taught kids when it was time to do factoring, and they were a little shaky with their math facts. We would tell them to go to the function screen, your y is equal to, this button here, go to your function screen, and type in whatever number. I used 144 with Adrienne just to show her, divided by all the numbers in the whole wide world. That's our x. And then if I go to the table of values, what I see is all of the different combinations of numbers that can be used in conjunction. That's an inverse variation. So famous inverse variation problems, you know, are going to be ones where you have that constant that's the output. So let's say that I'm having work done at my house, and we know that there's about 40 hours of work that needs to be done. I can have one guy come for 40 hours. I can have 2 people come for 20 hours. I can have 4 people come for 10 hours. I can have 5 people come for 8 hours. Did I get one? And anything in between. So those 2 values add multiply together. So you were supposed to see this for the first time when you were in Algebra 1, when they talked about inverse variation. And then if you press that graph, that's where you get your first exposure to, oh, because 144 is really crazy high. Let's go back and just make it 1 divided by x. When you press graph, that's where you get that crazy curved graph, and that's when I was teaching Algebra 1, I would make all the little middle schoolers giggle when I used the word asymptote, because they thought that was a really funny sounding word. And then they spent the rest of the day calling each other asymptotes. So there's, you know,
Yeah, it is pretty.
they just can't help but giggle at that word. And then they can't believe that's a real word. They're like, you just made that up. I swear to God. They think that, yeah. So, you know, then by the time you reach Algebra 2, you're like, I can't find the asymptotes. The horizontal and vertical asymptotes are going to be where that function is not defined. Here we have a horizontal asymptote at the x-axis. It approaches 0, never gets there. And then a vertical asymptote, of course, at the y-axis, because I'm never going to have 0 as an input. That makes my whole thing cancel out. So when you're in Algebra 2 and pre-calc, they talked about them being rational functions, and you spend a lot of time looking at how they moved all over, and they did funky things, or sometimes you had like them absent value or whatnot. So when I'm looking at this individual function, the output of that function when I put the x in is the height of my rectangle. The input is that change in x. And to be honest with you, when we're still talking this one, this is my change in x, because I'm taking the limit as x approaches 0. When I use my integral notation, the changes from the change in x to the delta, or to the d of x, is where the change in x gets so small. And we note that really tiny width of my rectangle with that d. This change is as this change in x approaches 0. All right. When I talk about my summation notation for this graph, I'm looking at my square root graph. And as I'm taking infinite Riemann sums, I'm taking the output of that radical, which represents that place, times however small my change of x is. And when I do the math on this function, it's going to give me that answer of how much that's worth underneath. And we'll talk about what that represents today. So whether I'm talking about it as a summation or an integral. Here we have a quadratic, and this quadratic gives you a nod to some of the transformations you had to do when your value is inside of the parentheses with the x. That's my left-right shift, and it is opposite of sign. So that means that, yeah. No, this is, there's no parentheses here. I like that better. Because this is a vertical shift, and it comes down 4. I like that better. Right?
Shouldn't the range be from 0 to 3, or is it?
Yeah. So this is from 0 to 3 because I'm not colored in back here at -2. That's a good catch. So here's my function of my Who said that? Go ahead, you can put Smarty up.
Why did we get rid of that?
So when we're talking about our shifts with our equations around the coordinate plane, if I have something that looks like this, where my x minus 4 is squared, that's where this is going to take it left, right. When I have my x is equal to x squared minus 4, this is going to take it up, down. This is tucked in with the x, this is not. So those parentheses, I guess they don't really make a difference because the squared is when the squared is outside, that's my left, right. So we can leave them in, especially since we're multiplying. I think that's why I put them there. There you go. Because it's being multiplied by the change in x. So I think they're okay. So I was okay on that, but I was wrong with the lower bound. Okay, let's see over here. So when I'm finding the cosine, your cosine graph is this one. But it's not from 0 to 2 pi, it's from negative pi to pi. So I went ahead and graphed it on both. I think I'm okay there. Yeah. And then this one, see how the negative 4, the minus 4 is inside the absolute value, that's what shifts this over this way. And then I have my interval from 1 to 3. Same graph, except for now I'm looking for my interval from 3 to 8. You okay with that? And then my sine function from negative pi to pi. Am I okay there? Awesome. So we're going to use the integral and we're going to define what we're going to call an accumulation function. And an accumulation function is what we're going to name that idea when we gather up all of those small rectangles and add their areas together and what that represents. All right, so last class we talked about the integral representing the area under the curve. So just to kind of put us all on the same page, this f of x was our height of the rectangle at that specific x value. So when we talk about that, whatever rectangle we're drawing, that's going to be its height at that specific value. This dx is going to represent the change in x that's very, 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 very small. And that's also the width of each rectangle. And remember, if I have an interval from a to b, including a and b, I found that by b minus a over n, which is the number of rectangles that I'm drawing to calculate the area. And this n represents our number of rectangles that I was drawing. So when we talk about this upper and lower limit, that goes along with the from A to B idea. With the integral notation, we don't have to talk about the limit as that change in x gets super, super small because we already have inferred that by using the dx instead of the change in x. But now it's time for us to talk about what this f of x represents. So this capital F notice we have this f function. There it is. We have this f function here. And these functions were our rate of change for something, whether it was the rate of the gallons being pumped into a tank or swimming pool, the rate of people coming in and out of a store, the rate of hot dogs on a plate, the rate of speed that you were driving, whatever your rate, that's what that little baby function is. Well, now we're going to start talking about, all right, well, what does this capital F function represent? And that's going to represent our area, and we're going to call it an accumulation function. So that f of x is that accumulation function that adds things up as we go. All right, so real quick, let's return some papers so that Isabella, Maria, Kenton,
Yeah.
Simon, why are you talking while I am? Simon, Grace, Stephen, Jaden. Anthony, Catherine, Kiara, Pete, Ricardo. Where'd Pete go?
He's not here.
He was.
He had a thing that happened.
Ricardo, Nadia, Veronica, Chloe. Chuck, Katie, Isabel, Stella, Adrian, Anthony, stop talking. Caitlin, Maria. Ineza, Veronica, Jacques, Caitlin, Haley. Oh, I think I did that backwards. Oh, yeah. Isabel, Veronica. Oh, this might be. Veronica, Simon. Now I need you, Isabel. Here's the student. And Veronica. All right. All right. So when you're looking at your quiz, I want to go through and talk about this a little bit, because this is what we mean by an accumulation function. When we talk about that first question, when you have talking about what that function means. So now we're going to talk about, we're looking at f of t, and that's our rate. And notice my integral has my lower bound, my lower limit of 0, all the way up to whatever value of x is given. And so we have to look at this interval here. So f of x is going to represent our accumulation function. So whatever it is that we are accumulating, that's what we're counting up, and that is what our capital F of x represents. So when I have an x value of 0, my f of x is 3, but my accumulation is 0. See if that makes sense to you. And here's why. At 1, I have covered an area of 1, 2.5. You have to leave your phone here. Just put it on the table, that's fine. Thanks. Hello. Thank you. All right, so now let's look at what happens at 2. Here we are at 2. My accumulation function, I get to look at this. I think it says now. Amazing. I think it says now. What does it say now? Now is now. So what do you think goes in that box? Turn and talk to your neighbors. Go. Why 4? Because this output is my accumulation function. What is the total of what I have here? You have 0 here, then you have 1, 2.5, plus another half makes 3, plus another whole makes. So at an input value of 3, what are your predictions? All right, let's talk about an input value of 4.
Taking it away. Yeah. So it's just gonna go back to 0? No.
Now what? Now what? So here's the interesting thing. Anthony's like, so wait a minute, it's just going to go back to 0. And then he looks down here and he goes, oh no, I'm going to continue to accumulate a negative change, but my interval is going to keep me with that cutoff point. You see that cutoff point there for my interval? Got it? Are we okay with that? Let's graph that. What do you say? All right, I say yes. I heard a yes. That's like the first positive thing I've heard today. I'm so excited. All right, so we have 0, 0. Here it is. We have 1. Let's graph 2.5. We have 2. We have 3. 4. 5. 6. I would like you to have a conversation with your group about what you notice. And then fill in those blanks. Go. What's the big deal with f of x? What is it? Big F of x, what is he? He is my, and guess what he is? What do you notice here?
He's a round guy.
Think back to the charts behind Caitlin.
It's the derivative. It's not the derivative. It's a different word.
Here's my derivative. What's this first one? That's my original function. In this graph, we took a position function. This is me throwing the ball up and throwing the ball down. The accumulation of change, no kidding, is 0. Because my derivative, remember that was my velocity? Up I go, down I go. Now, if this is something where you, a cannon went and the cannonball fired off of a ship back in the days of warfare, kerplunk down, it goes below sea level. Like maybe this can keep on going as it goes down, 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 down. Okay, I get that. But what we're talking about here is, f of x, that is my rate of change. That is my rate function. Remember we talked about that being our velocity function. So what's cool is by counting up the area, I'm counting up what it was that I was originally measuring. Height. If I took a ball and I threw it up in the air and it came back down, that ball has not really moved. Like it has that height up and down, but the accumulation of change is back to being 0 because we have this positive area and this negative area. So we're talking about this big F being our original function, our granddaddy of our function. This f of x is going to be our rate of change. So when we graph big F and little f on the same, we can see here I have a positive but decreasing velocity as I hit 0. Here's my rate of change at 0. And now I'm gaining speed, but I'm falling in a negative direction. Does it make sense to you that the derivative of a quadratic is linear? Does it make sense that the original function of a linear rate would be a parabola? So it's kind of cool when you see that way. All right, on to the other side. Let g of x equal, so g of x, this is going to be our accumulation. Our accumulation function. So that is going to be the area under the curve of g of t. So we want to use the graph and the figure to find the values of the table from -1 all the way up to +5. So our interval is from -1 all the way up to +5. So this one, so easy it's hard. Don't stretch your brain. At -1, what do I have? Careful. I have 0.
Oh, because it's our.
Now at 0, what do I have? Now at 1, what do I have? At 2, what do I have? At 3, 4, 5. Would you please take the time to graph the original function on this plane?
What is that?
Keep that thought in your head, it's a really good one.
Oh,
I'm gonna
oh,
come back to
0.
that in 2 seconds,
There we go.
right? So what would happen was all of these would go to programs, right? When you do parallel, and then you start taking the different things, we don't know the constant, and so that gives us an X, Y, and Z, it's a solution. So then on our increment, change the graph. We need some more information. Do you want to about the constant? Does that make sense?
Yeah, no. Valid.
Okay. What kind of graph did you get?
A line.
Yeah, it's a linear graph. So at -1, I'm at 0. -2, -4, -6, -8, 10, -12. So what's interesting is when I go to graph this function, I see it's a linear function. Would you call that a positive or a negative slope? Would you call it a constant rate of change? Do you see how this here is a negative constant rate of change? At -2, do you see down 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1? There's my rate of change. My rate of change is -2. That's my derivative of this, my original equation.
So is this just a new way to find derivatives?
We're
Of the graph?
given the derivatives. Now we're
Yeah,
going
backwards, but could you have done this, like, backwards to get the same thing? Is that even possible? Or am I just,
we're gonna do it backwards.
oh, no. Oh, that's,
All right, so g of x is the
that didn't make any sense.
original function. And keep in mind, it is linear. Linear. G of x is going to be our rate of change. And it's a constant because it's one tier, one power lower. Kind of cool, don't you think? All right, here's what I have for you. With your partner. Adrian, pop over here and work with. Brady, pop over here. Nate, pop over here and work with. David, you're like, Nate, pop over here and work with. Turn it. Did I give you guys everyone?
Yeah.
Did I give you guys two there? Okay, so do me a favor and separate out, you guys, are gonna work as a group of 4. Separate out, did I give you guys 2? Okay. Separate out your yellow and your pink cards, and let's just look at the pink. So make a pile of yellow, pink. And I would like you to just look at the pink cards for now.